All right, let's get right into it. We're going to tackle a question that drives everyone nuts, especially gamers and streamers. Why does my internet still lag even when I'm paying for a super fast connection? Well, the answer isn't just about speed. It's about the fundamental mathematics of how networks actually perform. And if you're prepping for an exam, this is the deep dive you've been looking for. We've all been there, right? You're paying for top-tier bandwidth, but you still get that frustrating lag. The reason is that the advertised speed is only part of the story. The real story is about the journey that every single packet of data takes to get from a server to your screen. And that journey, well, it has 4 very distinct speed bumps, or delays, that we really need to break down. Okay, so to really understand this, we're going to follow a single packet as it travels through a router. Every time a packet hits one of these nodes, like a router, it gets held up. It experiences a delay. Our job for your exam is to figure out exactly what causes that delay and how to calculate it. And that total time a packet spends just hanging out at one router is called the nodal delay. But here's the key. It's not just one big chunk of time. It's actually the sum of 4 totally different components. Once you can identify and calculate each of these, trust me, you can solve pretty much any network performance problem they throw at you. And here it is. This is the formula you absolutely need to burn into your brain. The total nodal delay is the sum of processing delay, queuing delay, transmission delay, and propagation delay. This is our roadmap for everything we're about to cover. So first up is processing delay. That's just the tiny amount of time a router takes to check the packet's header and figure out where to send it next. Then you've got queuing delay. That's the time it spends waiting in line if the router's busy. But the two that trip everyone up, the two that are almost guaranteed to be on your exam, are transmission and propagation delay. So let's tackle those head on right now. And I'm not kidding. Getting this distinction right is absolutely critical. Most exam questions are designed specifically to test if you understand the difference. So let's make sure it's crystal clear. Okay, here is the absolute heart of it. Transmission delay is all about the packet's size. It's the time it takes the router to push all the bits of that packet onto the link. Think of it like loading passengers onto a bus. Now, propagation delay is totally different. It's all about distance. It's the time it takes for the first bit to travel from one end of the physical wire to the other. That's the bus's travel time. So one depends on size, the other depends on distance. You know, to really make this stick, let's use the classic analogy from the Caruso and Ross textbook. Honestly, it's the best way I've ever seen this whole thing explained. So think about it this way. The transmission delay is how long it takes the toll booth guy to process all 10 cars and get them onto the highway. That depends on how many cars there are and how fast he works. But the propagation delay, that's just the time it takes the first car to drive down the highway to the next toll booth. It doesn't matter if there's 1 car or 100 behind it, the travel time is the travel time. All right, here's the math you need. For transmission delay, it's simply the packet length, which we call L, divided by the link rate, or R. So bigger packet or slower link, you get a higher transmission delay. Simple as that. And for propagation delay, it's even simpler. It's just the physical distance of the cable, D, divided by the propagation speed of the signal, S, which is usually pretty close to the speed of light. Okay, so we've handled the 2 delays that are pretty predictable. Now, let's get into the messy one, the part that's totally unpredictable and causes all the traffic jams. Queuing delay. Queuing delay is literally the time your packet spends waiting in line, sitting in a router's buffer because other packets are ahead of it. Now, if the network is totally empty, your queuing delay is basically 0. But if it's rush hour, man, it can be huge. And that variability is what makes network performance so tricky to predict in the real world. So how do we actually measure this congestion? Well, we use a really important metric called traffic intensity. Look at the formula. L times A over R. L is the packet size, and A is how many packets arrive per second. So L times A is basically the rate bits are showing up, and R is the rate bits can leave. So traffic intensity is just the ratio of how fast stuff arrives to how fast you can send it out. And this is where you see the real drama. Look at this graph. When the traffic intensity is low, near 0, there's hardly any line, no delay. But watch what happens as that ratio gets closer and closer to 1, meaning bits are arriving just as fast as they can be sent. The delay doesn't just go up a little bit, it absolutely skyrockets, heading towards infinity. And that right there leads us to the #1 golden rule of network design. If bits are consistently arriving faster than you can possibly send them out, your queue is just going to grow and grow forever. That's a recipe for disaster. So system designers always aim to keep that traffic intensity well below 1. But what happens if it does go over 1? Or what if there's a sudden burst of traffic that fills up the router's memory, its buffer? Well, since that buffer isn't infinite, when a new packet arrives and there's no room, the router only has one option left. It drops the packet. Poof. It's just gone. Discarded. This is what we call packet loss, and it's the direct result of a queue overflowing. That's why when we talk about network performance, it's always about two things: delay and loss, because high congestion is going to cause both. Okay, so let's zoom out for a minute. We've been super focused on the delay at a single router, but what you, the user, actually experience is the performance of the whole journey, right? From end to end. And that's where the idea of throughput comes in. So let's talk about throughput. You can forget all those fancy numbers your internet provider advertises. Throughput is the actual measured rate at which you receive bits from a server. It's the number that really determines your download speed or how good your video stream looks. The easiest way to wrap your head around this is to think of your internet connection as a series of pipes, all with different diameters. It doesn't matter how huge some of the pipes are, the total amount of water you can get through is always going to be limited by the single narrowest pipe in the whole system. In networking, we call that the bottleneck link. And the math here is actually super simple. If you have a path from a server to a client, the end-to-end throughput is simply the minimum of all the different link speeds along the way. You are always limited by the slowest link in that chain. And here it is, your exam cram sheet. If you're going to memorize one thing from this whole deep dive, this table is it. It's got all the delay types, their formulas, and most importantly, what they depend on. Processing is about router speed. Queuing is about traffic. Transmission is about packet size. And propagation is about physical distance. Know this table cold. So that really covers the fundamentals of delay, loss, and throughput. But I want to leave you with one final thought, a little brain teaser for your advanced studies. We've calculated the delay for one successful trip, but what happens to the total delay when a packet gets lost, like we talked about, and has to be sent all over again? That's where things get really interesting.